All right, welcome to day 75. Today, we're going to pop the hood on models like GPT and look at a critical piece of the engine, the transformer encoder block. You know, for a long time, language models bred pretty much like we do, one word at a time in order. Think of older models like RNNs. But then transformers came along and just completely changed the game. Instead of reading sequentially, they look at all the words in a sentence at the exact same time. Now, this is way faster, but it creates a really interesting problem. If you see everything at once, you actually lose something super important. So if all the words arrive at once, how on earth does the model know their order? How does it get that the dog chased the cat means something totally different from the cat chased the dog? That right there, that's the puzzle we're going to solve today. And by the end of this quick session, you'll get it. You'll understand the core mechanism that gives transformers all that contextual power, the encoder block. So the solution to our puzzle is something called the encoder block. And honestly, the best way to think about it is as a powerful context engine. Its entire job is to take in a bunch of words that are just isolated meanings, and then it injects the context of the whole sentence into each and every one of them. Okay, so how does this context engine actually work? Well, it's not some single magical black box. It's really a clever combination of three key parts working together. First up, we have something called positional encoding. This basically gives every word an address so the model knows where it is. Next, there's the famous part, multi-head self-attention. This is the mechanism that figures out how all the words are related to each other. And finally, a feed-forward network comes in to process each word's new context-rich meaning a little more deeply. Let's take a closer look at each piece. So remember our problem. The model sees all words at once and has no clue about their order. Positional encoding is the fix. It's a really neat trick, actually. We just take the original vector that represents the word's meaning, and we add another vector to it. This second vector doesn't care about meaning at all. It just encodes the word's position in the sentence. Yeah, it's literally just vector addition. You take the word vector for dog, add the vector that says I am in position 2, and boom! The resulting vector now holds both the what and the where. Just like that, the model has the ordering information it was missing. Okay, on to the second mechanism, which is probably the most famous part of the transformer. Take a look at this sentence. For us, it's easy. We get it instantly. But for a computer, there's a tricky little ambiguity hiding in there. The issue is that word, they. Is it talking about the friends or is it talking about the tomatoes? To make any sense of this sentence, the model has to figure this out. This is a classic challenge in natural language processing. And the solution is a brilliant mechanism called self-attention. What it does is, for every single word, it looks at all the other words in the sentence and asks a simple question. How important are you to me? It then calculates these attention scores to measure that importance. And here's what that looks like in practice. When the model gets to the word they, the self-attention mechanism lights up for the word tomatoes, giving it a super high score. It figured it out. They refers to the tomatoes. And that's how it cuts through the ambiguity. You know, a really good analogy for this is being at a loud party. Imagine you're the query. You're trying to figure something out. You scan the room, looking for people who seem relevant to your question. Those are the keys. When you find someone, you focus in and listen to what they're actually saying. That's the value. Self-attention is just a mathematical way of doing this, using what are called query, key, and value matrices. So why multi-head attention? Well, because looking at the sentence from just one angle isn't enough. The model actually runs this whole attention process multiple times all at once. Each head learns to pay attention to different things. Maybe one head focuses on grammar, while another looks for semantic connections. By combining all these different viewpoints, the model gets a much richer, more complete picture of the text. Okay, so after the attention step, every word vector is now packed with contextual information. The final piece of the puzzle is a pretty standard component, a feed-forward network. It takes each of these newly enriched vectors and just thinks about them a little harder, one by one. This lets the model dig deeper and pull out even more sophisticated features. Now, there are also two little utility layers that help everything run smoothly. They're called add and norm. You can think of them as the plumbing of the encoder block. They use something called skip connections, which is basically an express lane for information. This is really important because it helps prevent the original signal from getting lost as it goes through all this processing, which makes training the model much more stable. But here's the really important part. One encoder block on its own isn't where the magic happens. The real power comes from stacking them, one on top of the other. The output of the first block feeds into the second into the third, and so on. This creates a hierarchy of understanding. The first layer might learn simple word relationships, the middle layers might figure out grammar, and by the time you get to the top, the model is grasping really abstract semantic concepts. If you've ever worked with image recognition models, this probably sounds familiar. It's the same idea behind convolutional neural networks, right? The first layers see basic edges and colors, and later layers build on that to recognize complex objects like faces or cars. It's the same principle, just for language. Just as a reference point, the original Attention is All You Need paper suggested stacking 6 of these encoder blocks. Today's big models use a lot more, but the fundamental idea is exactly the same. So, after a sentence has passed through this whole stack of encoders, what do we have? We have a set of vectors. Each one still corresponds to an original word, but now it's been transformed. It's packed with a rich understanding of its own meaning, its position, and its connections to the entire sentence. So, why is this so important? Because this mechanism, this is the bedrock of how models like GPT actually understand language. It's the engine that powers everything from machine translation to text summarization. Those final context-rich vectors we just talked about, you can think of those as the raw material for the model's thinking. So let's just quickly recap. The transformer encoder block takes in words, injects positional info, uses multi-head self-attention to figure out relationships, and then stacks these blocks to build up a really deep understanding of the text. And if there's just one thing you take away from this, let it be this. It's the combination of processing everything at once, in parallel, with that clever self-attention mechanism that is the real magic here. That's what lets transformers see the entire context of a sentence simultaneously, breaking free from the limitations of older models. It's the secret sauce.